Um, I need to go through the recording afterwards. All right. Okay. All right. So let's keep going. So basically comparing means, that's what we're going to do today. In the first class, or was it the second class, we talked about what means are. A mean is basically an average, right? And we talked about how means are different from medians. And if we didn't talk about it in class, we probably talked about it in the SPSS lab in R, but we also have talked about it in the recording. So we all know what a mean is. Is there anybody here who doesn't know what a mean is? Because that's an important concept for us to get before we advance forward. Is there anyone who doesn't know what a mean is at this point? All right. So we all know what
Hello.
a mean is, and we know what. Yeah, please ask your question.
Yeah, sorry to ask my question. Sometimes I used to get confused between average and then mean. In when I'm using Excel to calculate it, you will see sometimes harmonic mean, geometric mean, and average.
Yeah. Yeah. Thanks for that question. So there are different types of means, and when we talk about an average, we're really talking about an arithmetic mean. That is basically an average where you sum up a number of values and then you divide them by the number of the values, right? You sum up each value and then you divide by the number of values. And that's the average that we're all familiar with, right? But there are other types of averages as well, the geometric mean, the harmonic mean. Those are beyond the scope of this class, and those are not concepts that we typically will come across, except if you're doing certain types of statistics. So, for instance, if you're working in biomarkers, sometimes it might be necessary to use geometric means. To date, I've never used harmonic mean in my work, so I'm not exactly sure. Maybe in physics, where you would use a harmonic mean. So when we're talking about averages, we're really talking about the arithmetic mean, and that's what most people think about when thinking about the mean. Okay, thanks for that question.
Thank you.
But we do know what the difference is between the mean and the median, right? The median is kind of like the mean, except that when you rank the numbers from ascending order, from the one with the greatest value to the lowest value, or the other direction, and the one that's in the midpoint, that's the median. So we know that already. But sometimes in statistics, we want to compare two means. Okay, we want to compare two means. Or we want to compare a mean with a different value. So I guess, can somebody give me an example, just anything that comes to your mind, of a set of numbers that you may have estimated a mean from before, or you would like to estimate a mean from? Anyone? It's important for the class to be as interactive as possible, otherwise we're not going to be able to make the most of it. HbA1c. Okay, HbA1c. So we can calculate the mean HbA1c if there are 200 diabetes patients in your clinic and you want to evaluate their HbA1c. Maybe you are starting a new diabetes clinic, and maybe that's an example that we can use for this class. We're starting a new diabetes clinic. Does anybody here not know what HbA1c is?
Please,
So
I don't know.
HbA1c, okay, excellent. So HbA1c is a measure that is used to assess how well controlled a person's blood sugar is, right? So typically when a diabetes patient is in clinic, so you only see it in the context of people who already have diabetes. It's not typically used among those who do not have diabetes, right? So when in diabetes clinics, a person's HbA1c will be assessed from time to time. It might be maybe every 6 months or every 3 months. And the clinician will want to see how well the HbA1c is coming down within a certain reference range, right? So That's what HbA1c is. And there are many other examples of continuous variables that we might be interested in the mean for. Does anybody else have any other example of a continuous variable that they might be interested in the mean of?
Like body weight or hemoglobin.
Body weight, okay. Yeah, body weight, that's good. So body weight is another interesting example, and it depends on the age that the person is, right? So the body weight of an elderly person is different from what you would expect as the body weight of a young man who is in his prime. And it's also different from the body weight that we expect of children, right? So, and even in children, there's multiple different body weights that you will be thinking about depending on how old that child is. So 2 5-year-olds might have different body weight expectations, right? So if you take in the context of a pediatrics clinic, right, you have patients, and maybe this is something that all children should undergo. Every child from the time they are born should have their body weight checked from time to time, right? So typically it's done when a child goes to immunization clinic, but at least once every year, even after the child's immunizations are complete, you should have the body weight checked. And there is something called, there's a chart that we usually use that will then pick where the body weight is on that chart, and you can figure out whether the child is growing very fast or growing too slowly. So, and that's another example of a continuous variable that we are very often trying to intervene on, very often trying to improve upon. And so that's another example that I'm going to use in the context of this class. So sometimes, say you started a clinic, it might be a child health clinic or it might be a diabetes clinic, and you want to be able to measure the mean of the body weight or the HbA1c for the patients in your clinic, and you also want to be able to compare. So you already have the mean. Say in your clinic, the children who are 5-year-olds have a body weight of 10 kg, for example, right? Or maybe 10 kg. Yeah, maybe 10 kg is okay. So children in your clinic have a body weight of maybe 10 kg, for example. And those children, you want to then compare. Somebody says to you that 10 kg is too low compared to what you would expect for the children of that age, right? So you want to be able to compare that 10 kg to some other reference, right? To some other reference and say, oh, the children in my clinic, on average, they are too small for their weight, for their age. Or it might be that HbA1c, maybe you're starting a new diabetes clinic in this city. Right? You're an endocrinologist, you just arrived this city, and you open the diabetes clinic, and so many patients start coming in. You measure the HbA1c for all these people. There might be maybe 50 patients in your clinic. And the HbA1c for all these patients is, let's say, 9, right? And so when you look at that HbA1c, you're thinking, this is very high. This is higher than what I would expect, right? But how do you know that that is significantly higher, right? You want to compare it to something called a reference. You want to compare it to another value. So that you have one mean, you want to compare it to another value. In some cases, you want to compare that mean to something else entirely, maybe HbA1c from another clinic. So maybe you're a doctor who just finished his residency, and in your new clinic, the HbA1c is 9. But you previously worked at a clinic where the HbA1c of patients on average was 7. How do you compare those together, right? These are all the scenarios where we're going to use, and the reason why I'm setting the stage for you is that there's going to be multiple scenarios where we're going to need to compare means. And that's one scenario is where you're comparing to a reference. The second scenario is where you're comparing two samples that are completely different from each other, but that you're comparing the same type of variable. So HbA1c in clinic A versus HbA1c in clinic B, or body weight among children who are in JSS1 versus children who are in SS3, something like that. But there's another scenario again where that which you typically find in the context of interventions, where you intervene. So you first of all measure the body weight on maybe body weight in children who are 3-year-olds, and then you start feeding them a high protein diet. The same group of patients, and you feed them a high protein diet, and then follow them up over time, right? And then you measure the body weight at the end. Maybe that end is 1 year after, and you compare the weight at the beginning to the weight at the end, right? That's another scenario where we will want to compare means. And it's important to understand exactly which scenario you're operating in to know which test you will be conducting. So let's dive in. So the first type of tests that we use to compare means is called the one sample t-test. The one sample t-test. And there's a number of ways that we can do this. But first of all, when do we use the one sample t-test? We use the one sample t-test so we have one sample, as the name implies, and you want to compare it to a reference. Again, you have one sample and you want to compare it to a reference. And I've given examples of that just now, where you have the mean HbA1c among diabetes patients in your clinic, and you want to compare to a reference range. Maybe that reference range is derived from a global standard, where researchers have said the HbA1c for patients with diabetes should be about 7. And you measure the HbA1c for patients in your clinic, it's about 9, right? So somebody says, how do you know that the mean in your clinic is different, significantly different from the reference mean, right? So you will then compare both of them and compare that 9 to that 7. But it's not just this 9 that you're comparing. The 9 is a summary of several numbers, right? The 9 is an average. It's a summary of several numbers. And one of the key intuitions, one of the key assumptions that we make when we're trying to do a t-test, right? And the t-test is what we use to compare means on average, right? One of the key assumptions that we're making is what's called the central limit theorem. The central limit theorem is the idea that when you take a sample, and I'll give you an example. Maybe I use an example to describe what I'm talking about. So you go to the childcare clinic in your city, and maybe typically the kind of patients that you will find in the childcare clinic in your city, maybe there's about 2,000 children who usually come to that clinic all year round. So you then decide that you're going to go to that clinic several times a year, and you sample patients from that clinic several times a year. And every time you sample, you measure the mean. Every time you sample, you measure the mean, right? So you go to this morning, you measure, you get a mean of 3.5. You go again, you sample, you measure, you get a mean of 5. You go again, you measure, you get a mean of 7.5. Depending, it might, for several reasons, you're getting different numbers. The idea is that when you repeatedly sample like that, you will get several means. Okay, you get several means, and those means together, it's what we call a sampling distribution. Okay, that's what we call a sampling distribution. Okay, that's what we call a sampling distribution, which is it's a distribution of the means that you're estimating, and you then take all those means and you take the mean of those means, right? So you have several means that you've estimated, and then you take the mean of those means and the standard deviation of those means, right? And you have a range of values. So typically when you do that, you will have a range of values. Some of them will be very high, right? Some of them will be very, very high. Some of them will be very low, and you'll have something called a normal distribution. Typically, right? This is what's called a normal distribution. You have values that are, so if you're taking weights that go from, say the means that you have go from 3 to 9, right? So you have a few times when you estimate your mean, it will be here. You have a few times when you estimate your mean, it will be here. Maybe the children who came that day are just too small. maybe it was a neonatal clinic, or the children who came this day are just too big, but most times you will get a mean, that's in the middle, right? And so when you have this distribution that goes like that, that's a normal distribution. Why am I saying this? Because this central limit theorem and the normal distribution, they are key assumptions that underlie our ability to estimate the t-test. Just know that this is the intuition that makes it possible for us to estimate the t-test. So because we then have these central limit theorem and the normal distribution, right, assumptions that we're able to make, we can then calculate a 95% confidence interval. Does anybody know what the 95% confidence interval is and wants to give it a shot? Just raise your hand or just speak up.
Hello. So 95%
Yes, please.
confidence interval means that we are 95% sure that our mean lies between that range, and we are 5% less sure or something like that, or not sure of our population.
So we're excellent, thank you. So we are 95% sure that our mean lies within this range, right? So I mean, the way to really think about it is that the probability that our mean lies between this range is 95%. So if you have a range, so that 95% confidence interval is a set of values, right, that go from maybe somewhere here, right, to somewhere here. You see that it doesn't cover the full range of the values, but it covers about 95% of the values, right? So if you have so if you have a mean, when you calculate a mean like that and it falls here, you'll say, oh, it's in the 95% confidence interval. Or if it falls here, but if you have a mean that falls here, then, it's still within that possible range of values, but it's so extreme that it's outside the typical range of the values that you expect to see. Abubakar, please ask your question. Abubakar, you raised your hand.
Yeah, I said I didn't understand this. You said that the standard deviation is the standard error of the population. The standard deviation of the random mean, so is the standard error of the population?
Yeah, it's so typically this is in relation to the sampling distribution. Okay, this is not in relation to when we usually talk about standard deviation. But when we have a sampling distribution, the standard deviation that we will obtain from the mean of the means, right? So we estimate a mean, multiple means. Each one here is a mean, okay? And we estimate the mean. The standard deviation that we obtain from that mean of means is the standard error of the population. Just throw it like that. Don't rack your head too much about it. If you want to understand why it's that way, you would need to take a course in statistical theory. Okay. Yeah. All right. So I just want you to know that this is the underlying intuition. And one reason why we're telling you about these assumptions is for you to know that when those assumptions are not met, your estimates might be wrong, right? So in statistics, you have to understand what we're really doing is that we're making a number of assumptions, and we're using those assumptions to calculate what we want to calculate, okay? And when those assumptions are not met, then our values might be wrong. Nancy, please.
Okay, sorry. Thank you for the lecture so far. But I'm sorry if I'm going to draw us back. I don't know how we come about this 1.96. Please. Don't know if you can just...
I haven't gotten there.
Explain.
Okay, I haven't explained that at all. Okay. Yeah, I have not explained it. So that 1.96, yeah. So this 1.96 that we use to calculate the standard deviation, that we use to calculate the 95% confidence interval, is from something called the 2 times of the standard deviation, right? So I just wanted to to just go through this very quickly, but when you have a sampling distribution like this, right? When you have a sampling distribution like this, you can partition this distribution into different, I'm not sure that this thing will be easy to explain without figures. So if you have this, so say you estimate the height of kids in a school, right? You estimate the height of kids in a school and you do this multiple times, you obtain a sampling distribution. When you have this normal distribution, which is a bell curve, also called a bell curve, you can have this curve go like this, right? And your value can either be in the middle like this. Forgive my poor drawing skills. Let me see if I can change the color. Yeah. So you have in this box, right? That's one possible range of values. But you can also have another box that goes like this, right? And then you can also have another box that goes like this. Okay? So you can see that we're going from narrower to wider. And we're going from maybe stricter rules to less strict. Okay? When you have a value that falls, and the assumption here is that the distance from here to here is 1 standard deviation. That means that if you calculate the standard deviation of this mean, right, then you can partition the normal distribution such that there can be at least 3 standard deviations on each side. Okay, and so if you go from 1 standard deviation on the right to 1 standard deviation on the left, so this is minus 1 standard deviation to plus 1 standard deviation. That's one box, and then you can go to 2 standard deviation, minus 2 standard deviation to plus 2 standard deviation. Okay, now we say that in general, if we go from minus 2 standard deviation to plus 2 standard deviation, this gives us a degree of confidence that the values that fall in that box, right, that fall inside this range will be significant. Okay, so when we have that alpha that we have calculated, that's what helps us to come up with that what we are interested in is the 95% confidence interval. Okay, that 95% confidence interval is based on this plus or minus 2 standard deviation. And the plus or minus 2 standard deviation, when you calculate it using the z-score, you will get 1.96. Okay. Again, what I'm saying, again, the plus or minus 2 standard deviation, when you go and when you calculate using the z-score, you'll get 1.96. That's how we come up with 1.96. I don't know if that's clear.
Okay.
Or if I've just confused you. Yeah.
Said you score.
It's
So
not
we have
clear.
to find out what you say.
It's not clear. Yes, I know. So here's the thing. I don't want, we still have a long way to go, and we're trying to pack a lot of things into this class. So I want to skip along, but the key intuition for you to know is that the 1.96, right? The 1.96 comes from 2 standard deviations, right? The 1.96 comes from 2 standard deviations, which comes from this distribution, which is this, when you go from this one in the middle, from this value to this value, which means that there are still some values that are outside this extreme. Okay, there are values that are outside this extreme. So let me explain that when you have a range of values that like this, and you have a range of values like this, if you have your value, if you say, okay, let me stop using value and use actual numbers. If you go into a school and you measure the height of kids who are in, say, the Form 1 or GSS 1 or whatever, in their first year of secondary school, most of them will be about 1.3 meters, 1.4 meters. Some of them might be taller, some of them might be shorter, right? Now, when you measure all when you measure the height of these kids and the mean is 1.4, for instance, meters, okay? You now find a kid whose height is 2 meters. Okay, and you find another kid whose height is 0.9 meters, which is kind of very short. Okay. If you draw this distribution among the kids and you find that the mean is 1.4, most kids fall between 1.2 and 1.6, right? But you have some kids who are 2 meters. Those kids who are 2 meters are outside the range, they're extremes. So what we're really interested in doing is sort of finding kids who are outliers. Okay. And so if you find a kid whose height is 2 meters, you will say that this kid is outside the range of confidence. That basically what you're saying is that if the mean of the height of the class is 2 meters, if you estimate the mean of the height of the class and it is 2 meters, then that mean is outside the range of that we're confident about. I don't know if this is clear. Or if you find a kid whose height is 0.9 meters, then you will know that the mean of that height is outside the range that we're really confident about. And so that's an extreme value is basically what we're trying to say. So we're really trying to find extreme values that give us confidence. Let's keep going and we'll come back to it. Okay. So the one sample t-test is a t-test where you have the mean of the height of the kids in your class, and you're comparing it to a reference range. Okay. And when you compare to that reference range, if the value of that mean lies inside the confidence interval that you construct, right, then you will say that if it lies outside the confidence interval, you say that it doesn't likely belong to the population. Let's get going. Okay, and I'll use this example. Now, you have in this example, you assume that you estimate the calorie intake for people for 100 people from your population. And then you calculate the mean of the calories from your sample and the standard error from that sample. So that means that you're calculating the calorie intake for these people again and again and again, and you calculate the mean, right? And then you then use that to construct the upper and lower bounds of the confidence interval, okay? But somebody then tells you that so say you obtain a mean of 2,100 calories, right? Or say you obtain a mean of, say you want to compare to, you think that people should have 2,100 calories intake, but the mean that you obtain is 2,800, and the confidence interval goes from 2,000 to 3,000, right? Because your 2,100 falls inside that confidence interval, then you can assume that 2,100 comes from the same population distribution. Okay, let's do this using so typically when we have when we're trying to do a statistical test, the first thing you want is to determine what the null hypothesis is, right? The null hypothesis is the hypothesis that you're trying to disprove. So someone tells you that the mean calorie intake consumed during Eid is different from the mean calories on regular days. So Eid is a Muslim holiday where people tend to consume a lot of food, right? So you would expect that the calorie intake will be higher. But somebody might tell you, you know, even though people tend to consume a lot of food, on average, it still ends up being the same mean. It still ends up being in the same ballpark, right? So you then say, oh, the null hypothesis is that the mean calories is not the same. And the alternative hypothesis that you want to then disprove is that the mean calories differ. That means it might be higher or it might be lower. Okay? So on regular days, the mean calories that you consumed was 2,100. And then you estimated the mean from 100 people on Eid, and this time you obtained 1,850, which is kind of lower, right? And the standard deviation is 300 calories. Okay? We will use that standard deviation and to calculate the standard error, and then use that to calculate the confidence interval. So the confidence interval is the mean plus or minus 1.96 times the standard error. Okay? And so we then obtain a standard deviation that goes from 1,791 to 1,908. And we then compare this reference mean to these two numbers and see, does this number fall in between these two numbers? In this case, 2,100 does not fall in between them. And because it doesn't fall in between them, then we will say that this is not likely to be from that population distribution. And so the 2,100 calories outside of the range, then we say that is significantly different. Questions about this one sample t-test? Did this example make it easier to understand, or did they make it more complicated? Yes, Nick. Please speak up. You have your hand raised.
If I get you correctly now, we're particularly doing this 1.916 just to even see if all the data we've gotten, if it even makes any sense to start with, to use to then continue to do our analysis. Would that be like what this is all saying?
Sorry, can you say that again? I didn't get it.
I said, based on the way you explain it, what I got from, apart from the mathematical thing, is like basically we are first doing this mathematical thing to even see whether the data we've gotten, does it actually even make sense to begin with? Does it show that it is from where we want it from? Does it resemble what is normal for that group? And then we can then now say, okay, it's normal, and then we can then proceed. Is that what it is? Thank you.
That's exactly, yes, that's what we're doing. So that we're trying to see whether the data that we have is what is normal. Yeah, that's exactly what it is. But that itself can be something that we are interested in. We might not want to do more. It might just be that you want to decide whether you should intervene. So maybe somebody said to you that people consume more food on Eid. And so you want to decide whether you should organize an intervention before Eid to encourage people to not eat too much. And then someone tells you, you know, before you organize that intervention, why don't you first of all see whether people are really eating more, right? So you can look at the mean and the standard deviation and then use it to compare to the reference. The reference is 2,100. And if you find that the mean, right, the mean intake is not much different, then you'd be like, oh, maybe this is okay. But in this case, you're finding it's even lower. So you might then say, well, maybe people are not really eating more and we should encourage them to eat more and eat, right? If these values were higher than 2,100, then you would say, oh, maybe people are eating too much right, then it doesn't matter. But if 2,100 falls in between these values, then you'll say, oh, people are eating just about right, and you don't want to bother. Okay, so that's the intrusion. I think we have other hands raised. So who else has? So attention, do you want to speak up? And please correct me if I'm not pronouncing your name correctly. Sudhya, do you still have a question?
Yes.
Hello.
Oh,
Hello.
hi.
Okay, let her go first. Yeah, please.
Okay. I was just trying to add to about the 1.96. I don't know if simply put, we can say that it is that value at which, like, if you take the table, the critical value table, where you find the 0.05, where you find the probability of 0.05, that's 1.96, that's as 95. I don't know how I can put it, but I think that's the critical value as which you find that probability of 0.05. So it tells you whether you can accept or reject whatever your hypothesis is.
It is, yes, you're right. That the 0.05, which is the alpha, right, is based on that 1.96 if you assume that the sample size is large enough. Okay. So that's another way to understand it. Let me show you. So this is the critical value table and for the T distribution. And if you have an alpha of 0.05, that's this one, okay? And typically we are interested in a sample size that is large enough. So this third row, keep looking at it. If the sample size is large enough, that would be about 30, right? Or maybe a little lower than that. And your alpha is 0.05, then the critical value of 1.96 will be somewhere around here. Okay. So large enough sample size, this is the Z-score, and you would have, so that's sort of like an intrusion. If you calculate the Z-scores, that's another way to think about it. But the idea is that 1.96 is what you will then use to multiply against the standard error. Is this helpful?
Yes, it is.
Okay. All right. So moving on. So I realize that a lot of people are stuck on that 1.96, but the idea is that 1.96 depends on your alpha, which is 0.05, which depends on how strict you want to be in your ability to identify the values of interest. Okay. So moving on. So that's the one sample t-test. So do we have questions about the one sample t-test? Any questions? Is there anyone who doesn't understand it?
Yes.
Okay.
Yes,
so,
sir.
Yes, please, Nancy, ask your question.
Yes, from the calculation, I can see that the LT is 300 divided by the root of n. Please, what's the n here, sir? Please.
The n is 100. So the n is 100. The root of n is 10, right? So the standard deviation of 30 divided by 10 gives you, 300 divided by 10 gives you 30. That's how we came up with the 30. Sorry, I skipped along so quickly. Is that clear now?
Thank you.
I hope so.
Yes, sir.
Yeah. Okay. Henry, you have a question?
Yes, sir. Thank you very much, sir. I just want to confirm that the values that we are using for this study was probably collected around that age period. And if we have gotten a value that is, after calculating the confidence interval, we have values that actually fall below or above, let's say, because right now we are having below, that actually falls
Yeah.
above the normal mean, the mean that we are comparing with, are we going to, is that going to spur us to say, okay, there is actually a significant, how, I'm looking for the right word to use so that we can push further with the study, to conduct the study?
So yeah, that's a good question. So what we're really interested in knowing is whether the values are different. That's the hypothesis that we are interested in this case. There are other hypotheses that we might be interested in where we might be interested in whether it's higher or whether it's lower, right? But in this case, we calculated based on whether we want to know whether it's different. So in this case, we can see that the numbers are different from the confidence interval is different from this reference, and that's all we're interested in. So we'll stop there. We'll say, oh, this is different. In trying to understand, we can say, oh, it's lower, and so you can then ask yourself whether you want to intervene to make it higher, right? Or if the values were higher, then you can ask yourself, do you want to intervene to make it lower? Okay. So that's the one sample t-test. And another way to calculate the one sample. So one way to calculate the one sample t-test is using the confidence interval. Another way to calculate the one sample t-test is to use the t-score, right? So you will calculate the t-score. So you will estimate the this value and use that to calculate the t-score, and then you will use in the t-test table this negative 8.33, for instance. You will then look at it in the t-test table and come up with a p-value. So you will use a p-value. But the truth is that in most statistics today, we wouldn't calculate by hand, and we will just use a software. And so I'll just skip along and just let you know that there are other approaches for us to calculate the t-test apart from comparing to the confidence interval. Another way is to use the t-score. But so if you use the software and you obtain a t-score, then you can go look at that in the t-test calculator and figure out the p-value from there. Abubakar.
Yeah, sorry, sir. Like for this null hypothesis, so is it like when we say null hypothesis, we are saying that there is no similarity between the given mean and the expected mean or random mean? So, but I am seeing we are crossing with the equal sign means that they are not equal.
Yeah, thank you very much for catching that. That is supposed to be that they are equal.
Yeah.
And that is why the next one says that they are different.
Yeah, that
right?
is the null and alternative. Yeah, I was so confused since the beginning. Then I said, okay, maybe let me clarify. Sorry for.
Yeah, thank you. Thank you very much for pointing that out. That should be, the first one is that the mean calories are the same. The second one is that they are different, right? So it could be higher or lower. We don't really care, but that's the null hypothesis we're interested in. All right. So I'm going to explain what the PET t-test is, and then we'll take a break. Okay. The PET t-test is the idea that you have two values, but those two values, they come from the same distribution. They come from the same people, not the same people, or the same sample, but conducted twice. Right. So the idea is that you measure today, you intervene, then you measure. You have a systolic blood pressure, for instance, taken while sitting, and then systolic blood pressure taken while standing. From the same people, that's the key thing, the same group of people, okay? So if you have from the same group of people, then that tells you that this is a paired sample t-test. It's paired because we have two measurements from the same group of people. And there are many examples of that. So body weight at the beginning of an exercise program versus body weight at the end. Okay. versus body weight at the end, and you have an infant who is admitted for severe acute malnutrition. So you measure their weight at the beginning, and then you administer the rehabilitation to them, and then you have their weight at the end of the program. Questions about this? This is a key infusion in t-test. So in t-test, you have to know whether it's a one sample t-test, whether it's a paired sample t-test, or if it's independent. We said that in the one sample t-test, you're comparing to a reference. In the paired sample t-test, you have two means, one mean in the beginning and one mean at the end. Any questions? Or is this intuition clear? Because this is a key step. And, what we're really hoping to be able to do here is to help you know when to conduct what tests, right? And then you can implement it in software. Gideon, please.
Yeah, so the PET test, I'm just curious because I think it can also be conducted on two different people with matched characteristics. So when you said this only before and after, I was just trying to be sure.
The PET test. So we match characteristics. What do you mean by match characteristics?
Okay, for instance, I could be checking systolic blood pressure in different group of patients, but they have similar characteristics. They could serve as pairs, but not like the matching is 100%, but they're still comparable.
Typically not, right? Typically not. So you would have selected them as pairs, right? So if you say you're doing a case control study, for instance, and you match people based on age and sex, right? And then you say, okay, we match these people, and so we can calculate the t-test. The problem is that there's a key value of the PET t-test that you're going to lose, and that is the causal inference you're able to make. Because once you use that approach, right, then there is confounding. And we talked about, I don't know if you guys watched the inference, the last video for the inference. Confounding is going to be an issue that the PET t-test will not address in that scenario. So I wouldn't advise it. If you preferably you want to use a PET t-test in the same group of people at 2 time points. Jamila?
Yes, thank you, sir. I didn't understand the last statement of deciding whether your measurements are paired or independent is the most important step.
Okay. Yeah. So it's a good question. So the PET, so basically when you want to say paired, we say something is paired if you have two measurements, right? You have two measurements from the same group of people. That is paired. Okay? If you have two measurements from the same group of people, that is paired. And the idea is, and there's a lot of examples where this is the case. So the typical example is in when you have an intervention or when you're observing two things over time, right? So if you have an intervention where you have body weight at the beginning of an exercise program and then body weight at the end, that is paired, okay? If you have body weight for patients in one gym, for people attending one gym, and body weight for people attending another gym, that is not paired, okay? That is independent sample. Yes, exactly. That is independent. And that's a very key infusion. And that's why I said that it's not the question that Gideon asked. Gideon asked whether if we match them, maybe that makes them paired. And I said, not necessarily, because there's a number of other factors that are going to be at play. So it's better to still think about them as independent sample and to use appropriate methods. There are some appropriate methods where there is clustering, where you might want to consider in the context of case control studies. So we can talk about that later. But in this scenario, if you have two measurements taken at 2 time points, that is a paired sample and you would use a paired t-test. Henry?
All right, sir. I just want to ask, for instance, someone that has lost blood and the PCV is very low, can we actually, can we say that checking the PCV before the commencement of treatment to actually build back the blood volume, and while she is progressing in the treatment, or this set of persons are progressing in the treatment to boost their blood level, we now check this level again, the PCV, after some time. We can liken that to a paired sample t-test as well.
Yeah, that's exactly correct. So you have one measurement at the beginning and another measurement, you know, at the end or at some time points during the follow-up. That's a paired t-test. Okay. Does anybody have any other example of a paired t-test that comes to their mind or they want to share?
Maybe pre-test, post-test models.
Sorry, can you say that again?
Pre-test and post-test.
Pre-test and post-test. Yeah, pre-test and post-test. So say you're doing a seminar, and in that seminar you're teaching people about HIV, for instance, right? And these kinds of seminars were really common in the early days, where you want to teach people about HIV and how to prevent infection, you know, and safe practices. And at the beginning, you ask them 3 or 5 questions, and at the end, you ask them the same 3 or 5 questions, and you're comparing, you know, to see how they did in the beginning compared to the end. Very simple, straightforward, but that's also a paired t-test. Excellent. So someone said OCUs and SBT before and after on pregnant women. So I think you've added one more variable. So you have systolic blood pressure. And so Gideon, can you explain this example so that maybe the rest of us can benefit?
Okay, so what I meant is, like, if you are checking oral contraceptive use and the systolic blood pressure on women before and after, like before they use the they use like the oral contraceptive, and after they use it, did it affect their systolic blood pressure?
Their blood pressure. Yeah. Okay. Excellent. Yeah. So you have before they use and after they use that. Yeah, that's a paired t-test, and you follow them up for a period of time. So this is very important intuition. And if you don't take anything else away from today's class, this is the most important thing to take away, whether a test is paired or independent, okay? Or when it should be one sample. So we've talked about pair or one sample, and now we're talking about the paired t-test. This is the math that underlies it, right? I will not go through it, and just let you know that the idea is to calculate a t-score that you then read against in the figure in that t-test table. And the degrees of freedom is n-1. But in reality, when we are doing it in modern times, unless you're a statistician, none of us is thinking about this, the math behind this. Instead, what we're thinking about is it paired? Is it not paired? When should I use which test? And then you just go do it in the software. Okay. What's really going on is that there's a mean, right? So you have 2 means, and then you subtract those 2 means, so you get a difference. So you have a difference that you're comparing to a null difference, right? So say the blood pressure, the mean blood pressure is 140 at the beginning, and then you give people antihypertensives, and then the mean blood pressure at the end is 100. So you have a difference of 40. That difference of 40 is this D bar. And there's a null difference, which is this. And this null difference, you might say that null difference is 0. That is, you don't expect the antihypertensive to work at all. You don't expect it to reduce the blood pressure. So that null D might be 0. So you then say 40 minus 0, that gives you 40. And then the standard error of this D bar is this. And then you divide. That's what's really happening in the background. That's how you get this t-test, this t value that you then look at in the 4-figure table. But we don't do that again. And, you know, typically you just run it in the software, and the software will give you the t value. It will also give you the t value as well, which is what most people are interested in. Okay, so just telling you what intuition is going on in the background. So let's take an example. So in this example, you are the new CMD at a hospital in Lagos, and you ask all the resident doctors how many hours they worked last week, and then you calculated a mean, right? So you obtained 72 hours as the mean, okay? 72 hours, and that's here. This is the mean, okay? And you can see that in this range, there's some people who worked 20 hours, some people worked 119 hours. So it goes very wide range, but most people are working on average 72 hours, which is a lot, right? The average person works 40 hours a week, but these guys are working 72 hours. That's almost double. So you're like, oh, we have to do something about this, okay? So there's a number of things that's happening right now. We have a mean, we have a sense of where we want it to be, which is a reference. So I'm going to ask the question now. So if you decide that you want to compare the mean in your study to the reference of 40 hours a week, which is what you expect that any decent adult should be working, what type of t-test would you use? If you're comparing the mean here to the 40, attention please.
One sample t-test.
One sample t-test, very good. Does anybody agree or disagree? Or maybe does anybody disagree with her? We're all in agreement that this is a one sample t-test. Is anybody not sure that this is a one sample t-test scenario? Okay, all right, so we all agree, one sample t-test. So you then decide that, okay, we have to do something about it. So you hire other staff, and then you shift some of the work the doctors are doing to them, right? So this is a concept that has been talked about a lot. People are saying task shifting, let's hire more staff that they're cheaper on average. We shouldn't have doctors doing certain responsibilities. So that's the approach that you then decide to do, so that that's what you can afford as a CMD. And then you follow them up after 12 weeks, okay? So after 12 weeks, you go back to the same doctors and you ask them how many hours they're now working, okay? In the first time you measured, you had 72 hours. But now when you measured 3 months later, you have 64 hours, okay? If you want to compare these two numbers, what type of t-test would you conduct? Anybody? Harry?
We are going to conduct a paired sample t-test.
A paired sample t-test. Very good, paired sample. So thank you very much, Bashir, Nancy, Henry. So paired sample t-test. I know that there are so many more people in the class, but I'm not calling on people because I'm not sure how comfortable people are to answer questions. So the best way for you to be able to engage is if whatever you know, you raise your hand, you speak up, and you get called. Okay, so that will be useful for everybody. But the thing that I want you to notice about this is, look at the table on the right. This table is that there's a range of values, right? Even the first time, some people go from 70, some people have 112. Yeah, and this is just 15 as an example, right? There's probably many more doctors at that hospital. And the same doctors, right? This doctor number 1 goes from 96 to 86 hours, right? This person goes from 79 to 73 hours. That's really what's happening. Some people reduce by 3 hours, 98 to 95, okay? Some people reduce by 112 to 96. It's possible that people might also have increased the number of hours for whatever reason. So, but we calculate the difference of the hours in week 0 versus week 12, and we get these differences. And you remember I said that these differences are what you will then compare against the null difference that we then use to get the t value that we use to get the p-value. Okay, so in this case, you then use SPSS. Does anybody not know that this is an SPSS output? Is this completely strange to you? This is the first time you're seeing these outputs. But this is SPSS. This is what the SPSS output will look like. It will probably be longer, but so you will have the SPSS outputs will have a breakdown of the paired sample statistics and then the test, right? So basically what is happening is that it's taking week 12 minus week 0 and estimating the mean of that, so that the mean difference, this difference, the mean of it is 7.86. That is this D bar. Okay, 7.86. And the standard deviation and the standard error are also calculated, and that is what we then have here. Okay, so we then use these numbers to calculate the t-value or the t-score, which we then check in the table to get the p-value. Okay, but we don't have to do that. We have it in SPSS has done it for us. And in this case, the t-value that we get is 28.35, and the p-value, the two-sided p-value, because remember that we asked for the null hypothesis of their difference. We're not interested in whether it's higher or lower per se, but if you're interested in the null hypothesis that the numbers are different, you would look at the two-sided p-value, and that p-value is less than 0.001. If you're interested in the null that the values actually increase, which is a one-sided p-value, that means you're only interested in numbers in one direction, that's when you will read off this p-value. Otherwise, you will just look at the two-sided p-value. Any questions?
Yes. I beg your pardon, the one-sided and two-sided p-value.
Okay. Yeah. So the one-sided p-value is a p-value that we read off when we're interested in only one direction. Okay, only one direction. That means that we want to see whether the mean of 71 or 72, we want to see whether that mean decreases only. That's our null. That's our alternative hypothesis, right? We're not interested. So, but what happens? What if the 72 became 90, right? The one-sided p-value will not be useful for you in this situation, because you're only interested in one direction. You're interested in the one direction that you have chosen, which is that it gets lower. Or you might choose one direction that it gets higher, but you're not interested in the direction that it gets lower in that scenario. But if you don't care what direction it went, you just want to see whether one is different from the other, right? Then that's when you will use the two-sided p-value. Most times in science, we use the two-sided p-value. Occasionally, we use the one-sided p-value, but most times we use two-sided. Abubakar?
Yes, sir. What I want to ask is about the t-score. So are we adding it to the mean or t-score?
No, we're not adding it to the mean. No, we're not adding it to the mean. We're just using it in the table. So the reason why I don't want to talk about this table too much is because we're not really using the table in modern times, right? Today, we're not really using the table in modern times. That's why I don't want to talk too much about it. But what we're really doing, if you learned statistics 20, 30 years ago, they will tell you that go and you get this t-value and you look at that table. I've shown you that table earlier today. And you look at that table, the critical values table, and you will then read it off. So this table, so the t-test that we got was 28.4. So you will look at that 28.4 in this table, okay? But we don't really use it again. I don't think I've used it myself in 10 years. So okay. I wouldn't ask you to bother too much. But what is really happening is that the software will go and check the table for you and use that to give you the p-values.
Okay.
Yeah.
Thank
So that's
you.
what's really happening. You're welcome. So somebody asked a question that the one-sided, the p-value we report depends on our research question. Correct. The p-value we report depends on the research question. If the research question is saying we're interested in looking at whether there's a difference, then we would report a two-sided p-value. If the research question is saying we're interested to see whether the number of hours reduced, which is one direction, then we'll report the one-sided p-value. All right, Henry.
Yeah, so you just answered my question with the last comment you made.
Excellent. I'm glad to hear that. All right. Any other questions before we move on? So moving on. So now when we have that, the t-test, we will then say that the difference in the mean hours worked was 7.9. Yeah, that's what we got here, right? Which is greater than 0, right? So it's greater than 0 means that there is a difference. There's really a difference. And 0 is the null. When we in the null, we said that there's no difference. So if there's no difference, that means difference equals 0, right? So in this case, we're saying the value is greater than 0. So that's 1. And the two-sided p-value was less than 0.001, this one. And we compare that to the alpha of 0.05. Okay? Compare it to the alpha of 0.05. And because this value is lower than that alpha, we reject the null. Okay? We reject null. We reject the null. And so when we reject the null of no difference, and then we conclude that there was a difference, that we conclude that we are shown that there's a significant difference. And in this case, we can see that the difference is lower, so we can say that they've significantly reduced the number of hours worked. Okay? Question, Sugar, please.
Okay, so on one-sided p-value, how do we know that it's going either down or up direction, or how do we manipulate it? Thank you.
Yeah, so very good. So one-sided p-value, basically read it against the p-value as well, right? So the question you're interested in is that it is lower. And so if the p-value is less than 0.01, then you also basically the same thing. You compare it to the alpha, and you look at how that number is related to the value of your null. So in this case, you would look at 7.9 and see, is it going in the direction that you're interested in, right? So if, for instance, the mean difference here was 7.9 but in the wrong direction, then you would, even though the p-value is less than 0.001, which is not likely, you will still say that the difference is not, because it's not in the direction that you're interested in. In fact, you will have calculated the t-test in such a way that it would account for that difference. So you wouldn't get a p-value less than 0.001 if the 7.9 did not go in the direction you're interested in. Again, this is not something that we typically do. If you want to do a one-sided p-value and you have questions about it for the t-test, you can reach out and then we can talk about it. But I don't want to confuse the class. Okay? So generally, the difference, look at the difference. Is it greater than 0 or is it different from 0? Okay, is it different from 0? And then and then you look at the p-value, is it less than the alpha of 0.05? If it's less than the alpha of 0.05, you reject the null. If it's not, you fail to reject the null. Oluchi? Please ask your question, Oluchi.
Hello, sir. Hello, good afternoon, sir.
Yes, good afternoon.
Sir, please, I don't know, is the 0 a standard? How did we get to that? Where is the 0 from? I don't understand. I'm lost.
The 0? The 0, yeah, okay, all right, very good. Excellent question. This 0 comes from Yeah, I think we just assumed that. I assumed that you would have gotten it. So this zero comes from the null hypothesis. So the null hypothesis that we had is that um, the null hypothesis that we had is that the mean in week one, okay, equals,
Okay.
this is not an equal sign, equal the mean in week 12, okay? And the alternative hypothesis is that the mean in week one is not equal the mean in week 12, okay? And
Okay.
if two things are equal, the difference is zero, right?
Yeah. Yes.
Do you agree? Yeah. That's where the zero comes from.
Yeah. Okay. 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 Is
Yeah.
that right?
Yeah. All right.
Okay.
So,
Thank you very much.
any other
Get it
questions?
now.
That's good. Yeah. So that's how you will interpret. But the other thing I haven't shown you is the confidence interval. Israel.
So is it a standard that the null hypothesis is zero, or it's just peculiar to this question?
It is usual that you would use a zero. This is usual. If you don't use a zero, then you're beginning to be in the one-sided p-value context, or you're beginning to be in some different context, right? Where you're going to have a minimum number, a minimum value of difference. But the typical thing most times is that the null hypothesis is zero. Okay? Most statistics that you will ever do, it will be zero.
Thank you.
In fact, I think that I don't think I've done anything where it's not zero. I know that the scenarios exist where it will be non-zero, but it's not usual. Okay?
Thank you.
All right. Yeah. So moving on. So the other way that you can interpret this is to look at the confidence interval. And so if you look at the confidence interval, remember we constructed the confidence interval when we use one sample t-test. We can do that here as well, right? Where we have the confidence interval for that mean difference, right? This is the mean difference. And the confidence interval here goes from 7.32 to 0.8 to 8.41. And we will compare this confidence interval again to zero, because zero is the null. Okay, zero is null value. And because zero is not in this range, zero is somewhere lower than this range, right? Is outside the range. We will say that the confidence interval does not include the null value. And so we reject the null hypothesis. So it means that the null hypothesis is wrong. Okay. Questions? Should we take a 2-minute break? So if you think we should take a 2-minute break, thumbs up. Otherwise, should we keep going? All right, so let's take a 2-minute break. And then we will come back in 2 minutes. So that basically just stretch out legs and yeah. All right, welcome back. I guess it's 2 minutes are up. So we'll take another example quickly. We're going a little slower than I anticipated, but yeah, that should still be okay. Henry.
Yes, sir. I have a question. Is there a
Okay.
scenario where we are going to have whereby the calculated p-value from our study would be will be greater than the alpha, and then we'll still have our confidence interval including the difference, I mean the value from the null hypothesis. Is it possible to have such?
I'm sorry, I can't hear you properly. I don't know if it's just me or if others can hear.
All right. Am I audible now?
Yes, it's better.
Right. I was saying that if it's possible to have, the value included in our confidence interval, but the calculated p-value being greater, because from what you said if the null value is not included after we calculate the confidence interval, we should reject the null hypothesis. And also from the example you gave, when the calculated p-value is less than the alpha, then we should reject the null hypothesis. I'm just asking if it's possible to have a value, p-value that will be greater than the alpha for a particular study, and yet the confidence interval will include that null value, if it's possible to have such scenarios. Thank you.
Okay, so good question. I think we talked about this a little bit in the SPSS lab. All right. So the thing is that the alpha of 0.05 is what we use to construct the confidence interval. And it's not possible for the p-value to be greater than 0.05, but the confidence interval then does not include the null. It will include the null. Okay? The p-value and the confidence interval are really the same thing. It's just representing it in different ways. If the p-value is less than 0.05, the confidence interval will not include the null. Okay? So that's why you don't have to use both the p-value and the confidence interval. You can use either one because they're really doing the same thing. Okay? Yeah. All right. So moving on. The second example. So the second example here is where we talked about systolic blood pressure, and say you're trying to test a new drug, and this is a very important. This is a common scenario in drug development where you're developing a drug for hypertension, and you're conducting a trial for 4 weeks where people are using the drug every day. Okay, so in the beginning, you measure the blood pressure, and you have 300 people. Okay, you measure the blood pressure, and you get 120. Okay, 119 plus 0.6. So you know what the mean is, you know what the standard deviation and standard error is. And then at the end of the trial, you have 117 in the same people. Does anybody not know which t-test we will use here? Does anybody know which t-test we'll use here? Which type?
Paired t-test, sir.
Paired t-test, thank you. So we will use a paired t-test. Does anybody have questions about that? Like I said, that's the most important thing to get from this class. The paired t-test, okay? And so using that, we want to interpret the results that we find here. And the null hypothesis is that the systolic blood pressure at the trial start is the same as systolic blood pressure in 4 weeks. Okay? So the null hypothesis is that the blood pressure at the beginning equals the blood pressure at week 4. Okay, and the alternative hypothesis is that the blood pressure at week 0, which is the beginning, is not equal to the blood pressure at week 4. Okay, so knowing this, can somebody tell us how do we interpret these results? Choose either the p-value or the confidence interval and interpret for us. Who's going to give it a shot? Anyone? This is the paired sample t-test. This is the output. So look at the output and interpret.
I think looking at the distribution, when we look at the mean, there is a 7.8. It means that there's a difference. And then we look at the two-sided p test, and we find that it's less than 0.05. The two-sided p where is 0.001, which means that it's a significant difference. So it then applies that. Hello?
Yeah, we can hear you.
Yeah, it then applies that for the trial, for this particular clinical trial, there is a significant difference between the blood pressure at week 0 and the blood pressure at week 4.
Week 4. Very good. Is there anyone who disagrees with this interpretation? Does anybody else want to try to interpret using the confidence interval? Yes, please, attention. Anyone? Gideon, okay.
Okay, using the confidence interval, we can say that we are 95% confident that the true population mean between those on week 0 and week 4 lies between 7.4 and 8.3, and we can see from our mean that it's actually within that range.
Okay, but would you say that this is significant? If you want to say that this is significant,
yes.
So you have described what the confidence interval is.
Okay, so it is significant, but it just H null because it's different than 0. So
it's different than 0. Yeah, because it does not. This confidence interval does not include 0, so it is significant. Okay, so that's very important intuition to get. Because this confidence interval does not include 0, then we say that this is significant. All right, so moving on. So we reject the null hypothesis. Israel, yes, go ahead.
So from what I used to know, and I'm asking this question for clarification, I used to know that the null hypothesis usually have there is no relationship between two between two variables. But now, like seeing that you're using the alternative hypothesis and you're saying that there's no relationship between two variables is quite confusing. Would you like to please clarify?
So the null hypothesis says that these are equal, right? So I think that the relationship, when we talk about relationship, this is usually in the context where we're looking at maybe odds ratios, risk ratios, okay? Where we're looking at whether there's a relationship between being a male versus having hypertension. That's where we talk about relationship. In this case, we're just looking at we're just comparing the means. We have two means from the same group of people. We're just comparing them. I want to see whether it's significantly different from zero or not significantly different from zero. That's really what we're doing. Or whether the means at each time point are significantly different from each other, which is really the same thing.
Okay, so
yeah,
when we're looking at the other kind of relationship, do we then say that null hypothesis would always be that it would always be there is no difference versus this particular one?
So when we say there's no relationship, that's what we usually use for the null in that context. We say there's no relationship. Here we're saying there's no difference.
Okay.
Right? So the null here is that there is no difference. In that situation, in that scenario, we're saying there's no relationship. And we'll get there from next week onwards. Okay? When we start looking at the relationship between variables. But right now, we're just looking at saying there's no difference. Okay?
Thank you.
Yeah, you're welcome. All right. So moving on.
Before you move on, please.
We're going to change
I
gears.
have a question.
Yeah.
Hello?
Please ask.
I have a question. I didn't understand that mean of
Jamila, please
7.
ask your question. Yeah. Yeah, what don't you understand?
Is it the mean of...
So here what we're saying is that there is a mean. I didn't get that. Can you say that again?
I was asking, is it the mean for the two means of the different blood pressures?
Yeah, if you subtract the mean blood pressure at week 0 to the mean blood pressure at week 4, the difference that you get is 7. And you can see that these numbers is about 7 point something when you subtract it, just eyeballing. So that's where that 7 comes from. And we want to see whether that 7 is significantly different from 0. Yeah.
All right. Thank you very much.
Yeah, you're welcome. Somebody else has a question. Shatima.
Good evening, sir.
Yeah, good evening.
Sorry, sir. Can you describe this table once again, sir? In relation to the null hypothesis, then also the alternative hypothesis. So based on this result now, which one are we going to?
So based on these results, there are two ways. There are two ways we can interpret. We can either use the p-value or we can use the confidence interval. Okay, using the p-value, we have a p-value of 0.0. And the first thing we have to do is we look at the mean difference, which is this 7.9, right? And we say that this is different from 0. Okay, so because it's different from 0, we want to see whether that difference is statistically significant. We then we compare it to the p-value. And in this case, we're interested in the two-sided p-value. And we'll say that because this p-value is less than 0.05, then we can confirm that this is statistically significant, and so we reject the null hypothesis. Okay? Another way that we can do this is to look at the confidence interval. The confidence interval goes from 7.4 to 8.3, and we see whether this confidence interval includes the null value of 0. In this case, the null value is 0. And because this does not include that null value of 0, we will say that this is statistically significant. Okay?
Thank you, sir.
So that's how to interpret it. Yeah, you're welcome. All right, so independent samples t-test, we can just skip along because you already know it. You've gotten an intuition of t-test. But the key question is, when should you use the independent samples t-test? So knowing everything that we've talked about today, does somebody want to tell us when should we use the independent samples t-test? Or give us an example. So someone, Gideon is asking, how about using critical value and t-statistics? Yes, you can use it. But so you can look at the t-statistic and go check it in the what's it called? But I don't typically bother about that approach. I use p-value and the confidence interval. Okay. So the independent one, the next question is independent samples t-test. Does anybody want to give us an example of when to use the independent samples t-test?
Let me try.
Okay.
Like in a West Africa examination exam, we're interested in knowing is there any difference between the score scored by a student in mathematics in two different schools. So we determined, we identified the score in school A, the scores in school B for West Africa examination. So we now compare the mean. Is there any difference between the scores students scored in school A compared with scores in school B? In school B,
correct. Yep. Excellent example. Scores in school A versus school B. The same variable is the scores, okay, but two different samples. Right. Mercy, you have a question? Or you want to give another example? Which one?
Yes, I have a question. Something I've been thinking about for a while. Okay, now the example that I give now is actually very perfect. So now I know most times when we do differential statistics, it should be okay. We want to use samples and not like population. So, but in this particular example mentioned, let's assume that we have the result of all the students. If it's easy to get the results, we can get the result of all the students in the two schools, and then we can do the mean and all of that. Does it still make sense to still now using any statistical test like the independent sample test to compare the means, or when we just get the mean, then that's just fine?
So that's a very interesting question that you have asked, right? So the question that she asked is that in inferential statistics, we said that we would usually use a sample. We usually use a sample. We cannot usually use the population to do our statistic, right? So she's then asking, in this case, since if we have a scenario where you can get the whole population, say you can measure everybody in the whole school, why should you then be using this statistical test, or you just look at the two means and compare them? The thing is that typically you will still use the t-test, and the reason for that is because although you think that at this point you're comparing two samples, but there's a lot of you're comparing two populations, but there is a lot of potential bias that is going into estimates. In general, in science, we believe that estimates are never perfect. There's always some measurement error that's going. There's always errors in how we're measuring. And so we want to acknowledge the fact that it's an estimate, it's not the truth. That's one. Two is that the fact that you're measuring the mean today in the samples of people who did the test this year, right? It doesn't mean that that's always going to be the value. And if you remember that very often when we're trying to use values in science, we're trying to generalize it to other scenarios. So say you wanted to compare two schools and you use the WAEC test, the West African exam test today, right? What we're really interested in is comparing the school over time. We're using today's values. For us to be able to compare the schools over time, we need to understand that this is an estimate of the truth, and so we would use the t-test as well instead of just comparing the mean alone. I hope that's clear.
Yes.
Basically, basically the idea is that the estimate, you're welcome. It's always an estimate, and so we would usually still use the test. Okay, all right. So the independent sample t-test is a t-test that we, that we conduct when we have independent samples, right? And the key intuition about independent samples is that it's not paired. And it's not a one sample t-test. It's two groups of people that are different in some way, right? So if you have a randomized control trial, and you have a randomized control trial, but that randomized control trial has one group of people assigned to treatment and one group of people assigned to placebo. So you have two groups. So you have group 1 and group 2, right? So because you have group 1 and group 2, that's already independent sample. And those groups are two different people, two different groups of people. That's independent samples. If you have people who are paired in some way, either because it's a 2 time points, then that's a paired sample t-test. Okay? At this point, it's useful to say that in the context of a case control study, which is the question that Gideon was asking before, where you matched people on some characteristics, it's not a true independent sample t-test because it violates the assumption that they are independent. Okay? And so you will use a separate kind of method that accounts for the fact that those people are matched in some way. But that's beyond what we're doing here. Okay? Here we're just assuming that two groups of people, the same value, and we want to compare the mean of that value in them. And the intuition about how we will do it is that we will calculate the mean in group 1 and the mean in group 2. We find the difference. Remember the other time, so we also found the difference, right? And then we will calculate the standard error of that difference. And when we divide this by this, we'll get the t-test. This gives us the t-statistic, which we can then go in multiple different ways. You can use that to look in the table and we get a p-value. We can compare it to a critical value, or we can construct a confidence interval, multiple different approaches. But the key intuition is that this is an independent sample t-test. This is when we have to use. But there's one more thing that we usually have to pay attention to in independent sample t-test, and that is what kind of standard deviation. Okay? Pay attention. Now, there are two kinds of standard deviations there's two ways that we think about the standard deviation in the independent sample t-test. We either want to know whether the standard deviation is equal or unequal. Okay? If we believe that the standard deviation, if we believe that the two groups are similar in most respects, so say you have a randomized control trial where you're the one who randomly assigned them. You have a group of people, you randomly assign them, and so you expect that the two groups are kind of similar in the characteristics, which is what randomization does. Then you would use an equal standard deviation. Okay? If you assume that the standard deviation, if you assume that the two groups are different in some way, then you will not be able to use an independent standard deviation. Some of those ways might be maybe two schools, right? We used the example of schools earlier. Two schools, and maybe you think that the schools are meaningfully different. One group is a school where the kids have always done very well in WAEC in the exam. Another school, the kids have not typically done well in the exam. You don't make the assumption that the standard deviations are similar. So you would think about it as an unequal standard deviation. Okay? In general, unless you're working in the context of a randomized control trial, you should consider using the unequal standard deviation method. Gideon, question.
Yes, I wanted to ask because, like in practice, what I've seen is like we usually conduct the Levene's test or the F test to first ascertain equality of the variances or the standard deviation. So I'm just wondering, like, can we just by guessing based on clinical characteristics that our standard deviation will be equal, or should we do the actual text to validate that?
You can do the actual test, yes. And I talk about that in the next slide. You can do the actual test. Okay, it's not here. But typically, the most important thing for you is to understand the scenario when the standard deviations will be equal or not equal. If it's a randomized control trial, you can assume that the standard deviation will be equal. If it's not a randomized control trial, you cannot assume that the standard deviation will be equal, right? Unless there's more things that are giving you that impression. But the key thing is that what do you understand? Right, so it's even right here, the test for equality of variances. So the key thing is the intrusion. For me, I think that if it's a randomized control trial, assume that the standard deviations are equal, move on. If not, do an unequal standard deviation. And here's the thing. If you assume that the standard deviations are not equal, but they are equal, you will still get correct answers. So if you're not sure, you can err on the side of unequal standard deviation, or you can check using the test for equality of variance, which I'm not going to teach because of time. But if you're not sure, right, use unequal standard deviation. Okay. The thing is that the way that the standard deviations are estimated is different. In the equal standard deviation, you're getting a standard deviation that is too precise. In unequal standard deviation, you're just assuming, it's kind of like you're waving in the air and thinking that this might likely be like a ballpark, right? And using that understanding that this is an estimate to move forward. Henry, I saw you raise your hand. Okay, hands down.
Yes, sir. I wasn't too clear about this equal standard deviation and unequal standard deviation. But from the question you answered that a colleague just asked, does that mean that if you are not sure, if you are not sure whether to use, if the distribution is a randomized control trial that was used, if you are not sure of it, you can just go ahead and use the non-equal standard deviation?
Yeah, that's what I'm saying. If you're not sure, you can use the not unequal standard deviation. If you're sure, because maybe it's a randomized control trial, then you can use the equal. Okay?
So please, I would like you to just definition of this equal standard deviation and the unequal, and how I've gotten some of the things you said when you mentioned that randomized control trial is most likely that the standard deviation is equal. I've gotten that aspect. The formula I'm seeing here, comparing to the formula of standard deviation, is the standard deviation that we have seen before is different. Is it? I don't know if you can shed more light on this.
The formulas are different because before, when we calculated standard deviation, we're looking at standard deviation in the context of one sample. Now we're taking two samples and we're pulling the standard deviation. Because you're pulling standard deviation of two samples, we need a different formula. And that's what this formula tries to do. Okay? So this is the standard deviation, one of the standard deviations that we have. This is the second standard deviation that we have. And now we're factoring in their own sample sizes, right? So we're factoring in their sample sizes in this case. And then that's what we're using to get this pooled standard deviation, okay? Now, if you look at the unequal standard deviation, we're just using the standard deviations and the n. It's not as precise as when you have the unequal standard deviation, and when you have the equal standard deviation. And, you know, the key thing for me, I think, is that if you're not sure, just assume that the standard deviations are not equal and use this formula. You'll still be fine. Your estimates might be just a little different, but that's it.
All right, thank you very much.
Okay. You're welcome. So, and you can practice it in your, you know, if you get a data set, you can look at the standard deviation. You can calculate the t-test using the equal standard deviation versus the unequal standard deviation. You see that there isn't much difference, you know, in what you will get. One is more precise if it's correct, right? So the question is usually like at the edges. So this is typically the scene where in some scenarios, there'll be scenarios where if you get it wrong, if you say that it is equal when it's not equal, you'll be wrong. But most times, if you just go with the unequal, then you'll be okay. Okay. All right. So this is an example, and really, this is an example where you randomly assign. So when it says randomly assign, you know that this is what kind of study. What's the study design here? Anybody? RCT, yes. So this is an RCT. And because it's an RCT, what do we want to assume about the standard deviation?
That
Anyone?
they are equal.
That they are equal. Yeah?
Deviation are equal.
Yeah, that the standard deviation are equal. So because of that, we would. So here, look at what SPSS does in this output. It gives you the value when the standard deviations are equal, as well as when the standard deviations are not equal. So you can see that you have two rows here. So let's look at the standard deviation not equal first. And here, this is the mean value that we have, right? And this is the p-value that we have. The p-value here is less than 0.05. So we know that this is significant. And when you compare the confidence intervals as well, right, it doesn't include 0. So we know that this is significant. In this scenario, if we had assumed that the standard deviations were equal, we will still have gotten the same answers because the confidence interval here doesn't include the null. The p-value is less than 0.05. Okay? So we will still have concluded that this is significant. So it doesn't really change, it didn't really change our results. The F-test here, which is what Gideon was talking about earlier, is that test of unequal variances. This test for equality of variances, right? And it says if the test for equality of variances is not significant, that is the p-value for the test for equality of variances greater than 0.05, then you can assume that the standard deviations are equal. Okay? So the p-value here is greater than 0.05. So that means that these standard deviations are actually equal. And so we can report the p-value on the first line and the confidence interval on the first line. But like I said, if you're not sure, you go with the equality of, you go with the assumption that they're not equal. But in this case, we're sure because it's an RCT anyway. So, okay. Questions? Any questions? Right, Margaret, please.
Okay, thank you very much. Please, would you explain the test of equality again? I didn't quite get it.
Okay, so usually when we look at the p-value, we use an alpha of less than 0.05, right? But for this, there's some statistical tests where we use an alpha of greater than 0.05. Okay? There are very few of them, but sometimes you come across them. This is one of those scenarios, and that's why I didn't want to go into it, because I don't want it to get confusing for people. But in this case, if the p-value that we get is above 0.05, then we will assume that the variances are equal. Okay? Then we will go with the values in the first row. If the p-values are greater than 0.05, in this case, which is 0.406, right? That's when we will use the first row as well. That's when we would assume that the variances are equal. But if it was less than 0.05, then we would assume that the variances are not equal and go with the second row. That's really what's happening here. But like I said, if you're not sure, just assume they're not equal and go with the second row. I hope that's clear.
Yes, thank you very
and
much.
Gideon was, yeah, very good. Yeah, okay. All right, so I'm going to skip this interpretation. Suga, you have a question?
Sorry, it was about the interpretation. So,
okay. So basically, the interpretation is the same way that we interpreted the previous one, which is the first thing that you do is that you look at the difference that you have, which in this case, this is the difference, the mean difference here, 0.8. And you look at that mean difference, is it different from 0? It is, right? So you say, oh, this mean difference is different from 0, but is it significant? That's the next thing. And so you would look at the p-value, the two-sided p-value, and in this case is less than 0.001. And because it's less than 0.001, which is less than the alpha of 0.05, we will say that it is statistically significant. Okay? And we will reject the null hypothesis of no difference and conclude that there was indeed a difference. Iron supplementation increased hemoglobin. Okay? That's the interpretation. The other way we could have done this is to look at the confidence interval and see whether 0 is included in that confidence interval. Okay? All right, so this is another example where you overhear two colleagues arguing about whether the number of works worked by male and female resident doctors were different. Okay? So you have the data you want to check, and you look at the number of hours worked for females is 62. So no, this is the number of females rather. You look at the number of hours worked for females is 68. The number of hours worked for males is 74 on average. Now, we know that you don't just check the means. You have to do a statistical test to help you see whether they're significantly different. So the first question is, which kind of t-test would you do? Is this a paired t-test or a one-sample t-test or an independent sample t-test?
So I think it should be an independent sample t-test.
Why?
Because we are checking the same variable but for two samples, the males and the females.
Two different samples. Excellent. Yep, excellent. Thank you. So independent samples t-test. Okay. Then the other thing that we then have, so we look at the mean. One is 68, the other is 74, a difference of maybe about 6, right? So it's a difference of 6. Now, you have this difference of 6, of negative 6.6. And so the next question you want to ask yourself is, which kind of standard deviation or variance should we use? Is it independent? Is it equal or unequal? Anyone? You have
So
a sample of. No, can you let somebody else answer? Thank you, Harry. I just want other people to be able to participate too.
Unequal?
Oh, unequal? Why is it not equal? Sugar, you want to try to explain why it's unequal? You're almost there.
Yeah, because the two groups, the two population, they're not similar. So we don't expect the standard deviation to be similar or at least comparable. So that's why.
Excellent, excellent. Yep. So unequal standard deviation. And then we will then use that, we will read off the two-sided p-value. Dr. Mubiko, thank you. It says that to err on the side of caution, we might also assume that the variances are unequal. So we'll read off the p-value 0.018, or we might look at the confidence interval. All right. Excellent. You guys are doing very great. So in the next 5 minutes, I want to talk about ANOVA, and then we'll wrap up for the day. Margaret.
Okay, sorry, please. For the last slide, looking at the where we talked about the test of equality, this 0.148, is it not greater than 0.05?
It's greater than 0.05.
Okay.
Very good. Thank you very much for catching it. Okay. Thank you very much for catching it. So this is why I said that, it's better for you to understand the intuition and apply it based on what you understand about the data. It doesn't necessarily mean that statistically it will agree. Okay? We have said that it is unequal because of what we know about this data. And that's correct. The data itself might not be much different. You see, what the statistic does is, what the F statistic does is, it uses the numbers that it sees. It doesn't know where the numbers are coming from. But we are going to use our own understanding of the data to assume that it is not equal. And we will be right to do that. Okay? And if we have the F statistic and it tells us, oh, this is a scenario where you could have assumed the quality, you will still be right. Okay? So there isn't like, in many scenarios, there isn't like this is, oh, if you don't do it like this, you're going to die, something like that. No, there is no, there is usually a little bit of flexibility as long as you know what you're doing and why you're doing it. So generally, I wouldn't even check the F statistic. I will just assume that it's unequal because this is coming from a scenario where I expect the numbers to be unequal. The numbers might then be equal for whatever reason because, because of the data generating process. But if I assumed unequal, I will still be right. Okay? Thank you very much for pointing that out. All right, so I want to talk about ANOVA very quickly because I think that, because we will not be able to come back to it, and it's useful to understand. Everything we've talked about today, we've talked about comparing two numbers. So we had one sample t-test where you compare to a reference range. We have peg t-test where you compare two numbers happening, one before, one after. And then we have independent samples t-test where you have two groups, where one group and then another group. But sometimes you want to compare more than two groups. And those two groups, it might be because of the nature of the variable. So in this case, you might want to check, maybe you have a group of people where, say in this class, you have people from so many different countries, right? And you come up with some classification and say, I want to see how the folks from West Africa are doing compared to the folks from East Africa versus the folks from South Africa, assuming everybody is from those three groups, right? So you would have three groups. Or you might want to say that you want to see so you want to see maybe calorie intake on Monday versus Tuesday versus Wednesday, or calorie intake on the 7 days of the week, right? Which is 7 groups. You cannot use a t-test because a t-test requires you to have 2 groups. Those are scenarios where you will then use an ANOVA. You will be able to compare the mean across the 3 or more groups. That's it. That's really what ANOVA is. It's really, think about it, the way I think about it is like t-test for more than 2 groups. Okay? That's the intuition. Of course, there's a number of things that are going on behind the scenes, but this is the null hypothesis for ANOVA, right? You're assuming that the mean in group 1 and the mean in group 2 are the same thing as the mean in group 3, you know, and all the way until group K. That is what you're saying, is that the means are equal. The alternative hypothesis is that at least one mean is different. At least one mean is different. So that might be that maybe 1 and 2 are the same, but 3 is different. Okay? So maybe the mean in 1 is 40, the mean in 2 is 42, and so you think, oh, maybe these are not much different. But the mean in 3 is 74. Okay? That's all ANOVA is checking, whether at least one is different. That's all. But it requires the same assumptions. That means that the data is normally distributed. The standard deviations are approximately equal. We haven't talked about that, mosquidasticity, but we also require that they are drawn independently. So this is not a paired t-test scenario. So if you're looking at the same group of people over time, but you have the means more than twice, you will not use ANOVA because there's some clustering and there's some tests that you will use in that scenario. Okay? And in this case, it's kind of like an independent samples t-test, but for more than 2 people, for more than 2 groups. That's ANOVA. Okay, and ANOVA is commonly used actually in science, especially in the context of like biomarkers, and so it's good to understand. And this is an example. Maybe these are examples actually that I haven't talked about them, where you have hemoglobin at delivery for people who are underweight, normal weight, and overweight, and you're comparing them. This is systolic blood pressure in group 1, group 2, group 3. Maybe group 1, you gave new drug X. In group 2, you gave new drug Y. And group C, you gave placebo, right? And you want to compare those 3 groups, then you would use ANOVA. Questions? Any questions? All right. So, Idris, you have a question? Please ask.
Yeah, yes, please. I have a question. Thank you very much. I want to be clarified one point you made. Is ANOVA used for just when you have 3 things to compare, or more than 3, or more than 2, like you said? Or is there a limit to numbers?
It's more than 2. Right, so that means that it can be more than, it can be 3, 4, 5, you know. But the issue is that if the numbers start getting too much, then you don't really know what it means that you're seeing. So typically, we wouldn't use ANOVA if the growth begins to be too much, right? Because again, the statistical power will break down. You will not be able to interpret what you're seeing. So yeah, so it's going to become hard. Okay. I want to stop here, but I won't take any questions. Maybe next week we might start with going through ANOVA very quickly. in some more detail, and then we'll take it from there. Any questions about everything we've talked about today? Yes, Deborah, please ask your question.
Thank you for your time. So my question is, I'm really confused. When do we use main confidence interval or test of equality? When do we use that?
The confidence interval we would use anytime we can use a p-value. Okay? If you can use a p-value, you can use a confidence interval. It doesn't matter. The test of unequal variance is a test that we use in the t-test, independent samples t-test, to decide whether we want to assume equal variance or we don't want to assume equal variance. Okay? So that's really how, yeah, welcome. Any other questions? So I'm going to assume that everybody understands everything that we've talked about today. Thank you very much for being very engaging. Henry, question or comment?
Yes, sir. Thank you very much for the lecture, sir. I want to confirm, you said that if you are not sure for the population, I mean, about if the population is going to have an equal standard deviation, I mean, the population of the sample that we can assume on equal. What if for a population whereby they are unequal and we assume equal? Is it going to affect the outcome?
It could, yes, it could. But very rarely. It could, but very rarely. So that's why it's, and you won't know what times those are, right? So it's always better to assume unequal unless you're sure that it's equal. Okay?
All right, sir. Then my last question is,
right.
Are there specific conditions where, apart from when we have randomized control trials, that we know that our sample will have equal standard deviations? Because someone sent on the group that for two different populations, it is, I don't know, probably that because the population is different, we cannot assume that the standard deviation is equal. Hence, we assume unequal standard deviation.
Unequal, yeah.
I don't know if standard, I mean, certain scenarios where we can be sure that the standard deviation is equal and unequal. Thank you very much, sir.
Yeah, thank you. So the issue is that it's the time when you can really be sure is in randomized control trial. That's when we can really be sure. Other times we cannot. By the design, by design. Other times we cannot be sure. Unless we test it, right, using the F-test. Or if you look at the standard deviations, I didn't talk about this, but this is another point. If when you estimate the standard deviation in one group and the standard deviation in the second group, and they don't look much different from the other, you might assume equal, but I think that the time when you really have confidence is if you have a randomized control trial. Other times, you're better off just assuming that it's not equal. What happens is that if you assume that it's not equal, you have a harder time of finding a significant result. And if you find a significant result, then you know that, oh, this is really good. But if you don't find a significant result, it might be because you didn't estimate correctly, it might be because your standard deviation was wrong, but you don't really care so much. The issue is that if you do find something that you know that what I'm seeing is real, it's kind of like the way to think about it. Okay?
Thank you very much.
You're welcome. Yeah. All right. So, Oluchi, I know that before you ask your question, I know that we're going to have SPSS in the next 15 minutes. So I want to make sure that people have time for a break before jumping off. Okay, Oluchi.
Yes, sir. Sir, please, I want to know if you have two standard deviations and then, okay, how will you say that they are actually different? Like, what's the value that maybe when they exceed, you can now say that not the same? Let me assume that you are being given you see two standard deviations. Let me say for instance, how would the value deviate from each other before you say that they are unnecessary or
Yeah.
they are
Yeah, that's a good question. The issue is that we don't have a particular value where we can say, oh, if it deviates from this particular value. But usually what we say is that if one is more than double another one, so maybe one standard deviation is 4, the other one is 8, then that's like times 2 of it, then then we will think that this is not equal, right? But if one is 4, the other is 5,
okay.
then maybe they're not much different. But in the end, it's a little hand wavy. It's not like it's not like a definite rule that okay, if it goes beyond this, then this is the rule. But we usually use double as a kind of general guide, so to speak. Okay.
Okay. Thank you, sir.
Yeah. You're welcome. All right, so we're gonna stop here and jump off. Thank you very much for joining the class. I'll see you guys soon.